I revisited pilot wave theory, and I've got to say, I was really surprised how impressive it was, especially since barely anyone talks about it. Think about the strangest features of quantum mechanics: wave-particle duality, superposition, wave function collapse, the measurement problem. It all led Richard Feynman to infamously declare that nobody understands quantum mechanics. But what if Feynman was wrong? What if all of these phenomena can actually be understood intuitively without all the weirdness of standard quantum theory? That's the promise of pilot wave theory. Pilot wave theory reproduces all the predictions of standard quantum mechanics while simultaneously resolving nearly all its famous conceptual issues. So why doesn't anyone talk about it? There are three reasons in particular why pilot wave theory is a minority view in the quantum community. But I must admit that while revisiting the topic for this video, I was surprised by how good the pilot wave interpretation actually is, and that its issues, apart from one, aren't all that bad. So today we'll run through three reasons why pilot wave theory is great, and three reasons why people still don't talk about it much. In 1952, I saw the impossible done. It was in papers by David Bohm. Bohm showed explicitly how parameters could indeed be introduced into non-relativistic wave mechanics, with the help of which the indeterministic description could be transformed into a deterministic one. These are the words of John Bell, a giant of the quantum age who ended up as pilot wave theory's most fervent supporter. And he's talking here about the first reason why it's such a great interpretation. Particles are located in definite positions which evolve deterministically. In standard quantum mechanics, particles don't have well-defined positions. They're smeared out in clouds of probability, so you can't ever predict exactly where a particle will end up in the future. As a result, standard quantum mechanics is indeterministic. But in 1952, David Bohm established the foundations of the pilot wave interpretation. He showed that you could reintroduce definite positions back into quantum mechanics without spoiling any of its predictions. So where quantum mechanics says that particles aren't actually located anywhere, pilot wave theory says that particles do have definite locations. It's just we're ignorant of them. We can't know for sure exactly where particles are because measurements are always uncertain and they interfere with the things they're trying to measure. But there is a matter of fact as to exactly where any given particles are. This sounds very unquantum, which is why Bell considered Bohm's feat so impressive. Pilot wave theory gives the same answers as standard quantum mechanics, but now its particles have a definite location, just like they did in classical mechanics. In addition, the particles move deterministically, so if you could know exactly where a particle was, you'd know exactly where it would be in the future too. All this is achieved by what's called the guiding equation, which is what Bohm derived. And this brings us to our second reason why pilot theory is great. Wave-particle duality is demystified. That particles sometimes behave as waves, and waves sometimes behave as particles, was always a tricky thing to get your head around in quantum mechanics. What is everything really? Waves or particles? The French physicist Louis de Broglie is famous for suggesting that familiar particles like electrons had wave-like properties, but he wasn't originally keen on the idea that reality was made up of weird particle-wave hybrids. So in 1924, at one of the Solvay conferences, de Broglie suggested that actually the world was made up of particles, but that they behaved like waves because they were carried or guided by the wave function, which was an actual wave. The idea didn't get a great reception, and de Broglie abandoned it shortly after. It took another 28 years before it was finally revived by David Bohm. And this is what his guiding equation is about. It tells you how the motion of particles are affected by the wave function. So in pilot wave theory, you have the wave function obeying the Schrödinger equation, just like in standard quantum mechanics, but on top you have the guiding equation, which tells you how the wave function affects the velocities of actual particles. So now we don't have to imagine the world as being made up of particle-wave hybrids. We have actual particles guided by an actual wave, the wave function. When describing the double slit experiment, Feynman called it a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. How does it really work? What machinery is actually producing this thing? Nobody knows any machinery. Nobody can give you a deeper explanation of this phenomenon than I have given. That is, a description of it. But the pilot wave interpretation does provide precisely the impossible deeper machinery Feynman is talking about. And that should be a sign of how impressive an interpretation it is. It says that particles, like electrons, only go through one of the slits, not both. But we still get an interference pattern on the screen because a wave, the wave function, goes through both and interferes. Wave-particle duality is no longer mysterious. But perhaps pilot wave theory's biggest achievement is that it resolves the central mystery of quantum mechanics, the measurement problem. When you don't look at a quantum system, it evolves according to the Schrödinger equation. When you do look at a quantum system, its wave function collapses into a definite state. The central issue of standard quantum mechanics is that these two behaviors are contradictory. Why does measurement suddenly produce completely different behavior in a quantum system? In theory, this could be resolved if we have a proper account of the measuring process, but this isn't possible in standard quantum mechanics. If you try to model the experimental apparatus along with the system, then the apparatus itself ends up in a quantum superposition, and you don't get definite outcomes. It's therefore exceptionally unclear why anything we observe has a definite outcome, when standard quantum mechanics tells us that everything should always evolve in superposition, in a mix of states. Pilot wave theory, on the other hand, completely resolves this. There's no sudden switch from one behavior to another. At all times, the evolution of the world is dictated by the Schrödinger equation, which, through the wave function, then itself dictates particle velocities through the guiding equation. So if the Schrödinger equation always holds in the pilot wave interpretation, then how does it account for wave function collapse? It's all down to how the environment interacts with the system. In pilot wave theory, you can distinguish between the wave function of the combined system and environment versus the wave function of just the system. The wave function of the system is called the conditional wave function, and it's obtained by taking the wave function of the combined system and environment and inputting the known positions of the objects in the environment, i.e., the measuring devices. What one finds is that when the measuring devices are not interacting with the system, the conditional wave function itself obeys the Schrödinger equation, as we might expect. But when a measurement is made, although the overall wave function must always obey Schrödinger's equation, the conditional wave function does not. Instead, it collapses in such a way that the particle is almost certainly to be found at one location or in one state. This solves the measurement problem because the whole system always obeys the same rules, and wave function collapse can be explained via the interaction between a system and measuring devices and the effect it has on the conditional wave function. The reason why pilot wave theory is able to do this, but standard quantum mechanics can't, is precisely because of the addition of definite positions. In standard quantum theory, there is no such thing as the actual configuration of the environment, and so it's impossible to disentangle the environment from the system being observed. By introducing definite positions, pilot wave theory is able to distinguish between system and environment, and it's this that leads to the collapse of the subsystem's wave function. The biggest conceptual issue in quantum mechanics isn't solved by pilot wave theory, it's completely sidestepped. It's just not a problem to begin with. And so, very impressively, pilot wave theory is able to come to precisely the same predictions as standard quantum theory, but without all the quantum weirdness and conceptual issues. So why isn't everyone a Bohmian pilot wave enthusiast? Historically, there are three main reasons why, but surprisingly, two of them are not nearly as bad as they first seem. The first reason pilot wave theory is typically shunned is because it is manifestly non-local. It's time to welcome John Bell back onto the scene, but in a rather unexpected role, considering he's supposed to be one of pilot wave theory's biggest supporters. And that's because in 1964, Bell produced his famous theorem, which many physicists erroneously thought ruled out theories like pilot wave. Bell's theorem has a history of misinterpretation, but a reasonable statement of it is that no local hidden variable theory can reproduce all the results of quantum mechanics. Now, pilot wave theory is a hidden variable theory because it introduces variables over and above the wave function, namely the exact positions of particles. It's slightly unfortunate that these are called hidden variables because one could argue that there's nothing particularly hidden about particle positions. They're directly measurable within a degree of uncertainty. But in quantum mechanics, any variables introduced in addition to the wave function are considered hidden variables. Now, many physicists interpreted Bell's theorem as ruling out interpretations like pilot wave theory because it's a hidden variable theory. But that's completely wrong. Bell's theorem doesn't rule out hidden variable theories. It tells us that no local hidden variable theory can reproduce the predictions of quantum mechanics. By local, we mean a theory in which objects are only influenced by the objects in their immediate surroundings. So if it's just that no local hidden variable theories can reproduce quantum mechanics, well, that leaves the door open to non-local hidden variable theories. And that's exactly what pilot wave theory is. It's a non-local hidden variable theory. And as such, it can reproduce the predictions of quantum mechanics exactly. But even if physicists had realized pilot wave theory wasn't ruled out by Bell's theorem, many would have been uncomfortable with the way it is non-local. Non-locality enters into pilot wave theory through the guiding equation. In the guiding equation, velocities of particles depend upon the instantaneous positions of all other particles. That's when the wave function of the system is entangled. In other words, in an entangled system, the particle velocities depend on the positions of other particles no matter how distant they are. Now, locality has always been one of the supporting pillars of physical thinking. Physicists really don't feel comfortable with theories in which distant objects can have an effect on each other. The fact that the guiding equation clearly contains the position of all particles at a precise moment flies in the face of locality. As a result, it's said that pilot wave theory is manifestly non-local. But is this situation all that bad? What's often forgotten is that quantum mechanics itself isn't local. You can have entangled states where separated particle spins seem to act on each other instantaneously. This is the so-called spooky action to distance. So in both standard quantum mechanics and pilot wave theory, there are non-local effects. But it's also true for both that you can't use these effects to transmit information faster than the speed of light. So is there really a problem? On the one hand, the non-locality in pilot wave theory is of a kind that physicists really don't like. A physical equation, the guiding equation, relates particle velocities to the positions of possibly distant particles. But on the other hand, quantum mechanics itself is already non-local, just in a more subtle way. In fact, Bell praised the non-locality in pilot wave theory for being more obvious. He said that the guiding wave, in the general case, propagates not in ordinary 3 space, but in a multi-dimensional configuration space, is the origin of the notorious non-locality of quantum mechanics. It is a merit of the de Broglie-Bohm version to bring this out so explicitly that it cannot be ignored. So yes, pilot wave theory is non-local. Particle positions everywhere seem to instantaneously affect the evolution of a single particle's velocity. This isn't the most appealing result, but since ordinary quantum mechanics is already non-local, perhaps it's unfair to mark pilot wave theory too harshly on this front. The second reason everyone isn't a pilot wave theorist is that pilot wave theory is not Lorentz invariant. Lorentz invariance is perhaps the centerpiece of special relativity. It demands that the laws of physics don't depend on the speed of the system. It doesn't matter if you perform an experiment in a lab stationary on the surface of the Earth, or in an aeroplane without turbulence soaring through the sky. It's a consequence of the 2 postulates of relativity. So, if pilot wave theory isn't Lorentz invariant, that's quite a big problem, because it means it's incompatible with special relativity. The origin of this incompatibility is actually in the non-local character of the pilot wave interpretation. We talked already about the fact that the guiding equation depends on the positions of all the particles in the system, no matter how far. But the question is, at what time? In special relativity, Lorentz invariance entails that there's no unique present moment, which means it's a real headache for pilot wave theorists that the guiding equation depends on the positions of all particles at a specific moment. Which moment? Understandably, incompatibility with special relativity was seen as a big problem for pilot wave theory. But here's the thing. Ordinary quantum mechanics is also incompatible. We've seen already that ordinary quantum mechanics is non-local, and in addition, wave function collapse in the theory is supposed to be an instantaneous process, something that happens to the whole system at the same moment. So it also clearly violates Lorentz invariance. So this also doesn't seem like a great reason to dismiss pilot wave theory in favour of the standard interpretation of quantum theory. But it brings us on to our final reason that pilot wave theory is hardly discussed, which is that quantum field theory is a huge success. As we've already seen, standard quantum theory and pilot wave theory share similar difficulties. They're both non-local and they're both incompatible with special relativity. As a result of this, one of the major breakthroughs of 20th century physics was the development of quantum field theory, a quantum theory which reworked standard quantum mechanics so that it incorporated relativity and explained various known phenomena such as particle creation and annihilation. Since then, quantum field theory has resulted in the creation of the standard model of particle physics, which is often touted as the most accurate scientific theory of the world ever produced. And this is the thing. Quantum field theory, this incredibly successful pillar of modern physics, is considered a unitary quantum theory. In standard quantum mechanics, unitary evolution refers to the evolution of the wave function according to the Schrödinger equation. In quantum field theory, it means that quantum states evolve in basically the same way. And here's the crucial point: without involving any rule for wave function collapse or any hidden variables. It achieves all of its successes with just the unitary evolution of quantum states and no further ingredients. So, because it's now compatible with special relativity, quantum field theory is a fundamentally different theory to ordinary quantum mechanics, and hence to pilot wave theory. And it works without introducing particle positions and without any rule concerning wave function collapse. By contrast, although there have been successful attempts to create pilot wave theory-like models that reproduce some of the predictions of quantum field theory, there's nothing that comes close to the standard unitary quantum field theory. In the words of the philosopher of physics David Wallace, unitary quantum mechanics stands unrivaled as our empirically most successful theory of the quantum domain. No extant version of Bohmian mechanics and no extant dynamical collapse theory succeeds in reproducing more than a small fragment of its predictions. And so I think that is the essence of why pilot wave theory doesn't receive much attention these days. If you compare it to standard quantum mechanics, then I think pilot wave theory does very well. It's conceptually much clearer, resolves some of the most pernicious conceptual problems, and suffers from no deficiencies not already suffered by ordinary quantum mechanics. So it almost certainly deserved more attention in the early days of quantum theory as a serious contender to ordinary quantum mechanics. But the simple fact is that time has moved on. Our most fundamental theory of the microscopic world is not quantum mechanics, but quantum field theory. And it is a theory without explicit particle positions. And while there are pilot wave-inspired theories that can reproduce some of the phenomena of quantum field theory, there's nothing that comes close to explaining as much as unitary quantum field theory can. So, until something comparable comes along, it's unlikely that this fascinating interpretation of basic quantum theory will shape our understanding of the world at its deepest levels any further. Thank you very much for watching, and I hope you enjoyed. Please like and subscribe for more Shots in the Quark.